To everyone and the good day. So welcome back on the second day of this workshop on impact evaluation method, difference in differences approach. So we have Dr. Oleg with us for the second day to take you forward with the practical session on the understanding the applications of the difference in differences approach. So with the very productive sessions that we had yesterday on the foundations and the estimations of the difference in difference method and discussion on the intuition and the assumptions related to this approach. So we proceed forward with the today's session. And before we initiate the session, so I would like to give you the house rules. So for speakers, as we already know, please turn off your video and the mic for all the time. When time allows, we will take up the question and answers. Chat box is available between speakers and the host. For audience, chat box and raise hands are not available. Please type your questions in the Q&A box at the bottom of the Zoom. So for the today's session, since it is most of the session will be a practical discussion on the hands-on training with the Stata. So please post your questions in the Q&A box and we'll take up as we go. Comments are not available in the Q&A box. Event may be photographed, streamlined, or video recorded. By attending, accepting connection, or continuing participation in the event, participants thereby consent to the possible use of their name, likeness, voice, spoken, or written comments, or papers, presentations in whatever form in all media publications, video sharing, websites, recordings, disseminations, or other external affair purposes for the Institute without compensation or permission. All sessions will include practical demonstrations using the software. Participants must have the software installed on their laptops prior to the training. ADBI will not provide software subscriptions. So I welcome Dr. Oleg Badunenko from Brunel University of London once again for today's session. Over to you, Dr. Oleg.
Thank you very much for a kind introduction again. The first things first, I just wanted to make sure that everybody can hear me all right.
Yes, we can hear you, Professor.
Yes, okay, great. So that's absolutely fine. So without further ado, let me just share the slides again, and we'll finish where we left off yesterday. So just let me know if you can see. Let me just move things around because it's really not a huge screen on my Surface. So can you see the full screen?
Yes.
Okay, great. Okay, so I will not take a lot of your time, as Dr. Rashida has correctly pointed out. The main reason for today's session is the hands-on approach using the software and implementation of principles that we considered in our conceptual part. So let me just very quickly run through where we stand. We use the multiple time periods, and we have three main assumptions that we are making in this setup. And as I will emphasize it many times, using this data, also the two data sets that we are going to consider, is that it's really important to understand the economic principles, economic setup of what is actually being performed. So the first assumption refers to here to staggered treatment adoption, implying that once a unit has been treated in a group, it remained treated. So it cannot be a temporary exposure. It's a permanent exposure. So if an individual has been treated in year 2, as just shown here, then this individual gets treatment all the way until the observation period. Okay, so this is the staggered treatment adoption. The second is the parallel trend, and in plain English, it means that in absence of, so suppose that there were some units or observations that were treated. And what this assumption tells us is that in the absence of treatment, the treated units would have evolved like never treated ones. And very briefly, if we have, for example, the evolvement for never treated units. So let me just take the blue color. So this is the never treated unit. Yeah. And we have the treated unit. So they perform like this. Now, in the absence of treatment, what this assumption tells us is that in the absence of treatment, they would have performed like the never treated units. So their performance would be parallel to what never treated units show, right? So that's why the term parallel trends. Now, we also noted that it's not necessary to assume conditioning on X, but this is basically only true for randomized controlled trials where the assignment into a treatment is completely random. With our observational data, we necessarily need to make the conditioning on X. And I have given you a flavor of what it means that something is conditioned on X. We split our sample into small portions, and within that small portion, there is an independence assumption. Now, the second part of the parallel trends is that the performance of the treatment or treated groups, if they were not treated, they would evolve as those who were not yet treated. So we have two parts of the parallel trend assumption. And the third main assumption is no anticipation and overlap, meaning that there is no changed behavior for units before the treatments begin, right? So basically, what it means is that what we want to observe is, suppose that this is the performance of the treated group, right? And suppose that this is the performance of the, so this is treatment, yeah, the treatment. So what we observe here is that the effect on the treated group begins after they were treated. We do not want to have a situation where this trend started before, right? So we do not want to have a red time of performance where you see the difference between the treated and not treated groups actually happened even before treatment. So we do not want to see anticipation in being treated, right? That would violate the assumption needed for identification. The next assumption here is overlap, and we have seen already how important this assumption for identification, right? Especially if we use the imputation type methods, which are very common nowadays in event studies and difference in different estimators. Okay, now given these three assumptions that we have made, we want to look at the group and time average treatment effect on a treated framework. So suppose now here capital G denotes a time a unit I has been first treated, right? Remember our staggered treatment adoption. So they were treated at some period of time and they remain treated. So GI is the time when an observation is first treated. And then we can define a group time, AT&T. So this is the difference between the observation performance in the treated state less the performance in the control state, starting for the treated period and afterwards, right? So basically, when we say this second on the treated part in the average treatment effect, it means this, right? So this capital GI equals G is the determination of the being treated. Now, the parallel trend assumption here in this group time framework is again, so this is the equivalent. So we can think about this as D equals 1 in our previous setup, right? And here the C never treated is an equivalent of the assumption that, not assumption, the setup that D is equal to 0, right? So what we are saying is that in this parallel trend assumption that those that were treated and those that weren't treated had the same tendencies, right? Now here C implies never treated, or by the same token GI equals plus infinity, so that it may be treated somewhere, very far in the future, right? So that's the same notation. Now, the core idea behind estimating the group and time average treatment effect on a treated is that we need to calculate this measure here, right? So we can use the never treated or not yet treated groups as a control group, okay? So this is the main idea that we can use here. And the difference in different style estimator is given in equation in the middle of the slide here. So remember that, again, these indices here are equivalent to the condition that observation is treated, and our C never treated condition is equivalent to in our previous notation that observation is in the control group, right? And so this is our control group here. Now we assume parallel trends between group G and comparison group, which is either never treated or not yet treated. And we can repeat it for each and every G where G is smaller than the small t, right? And finally, what we want to do is we want to obtain the covariate adjusted, which is the conditional DID or doubly robust estimators. So this is the core idea. What other estimation methods for this average treatment effects? Now, the three main approaches that we can relate to, and we have considered them in our estimation part here in our slides, is the regression outcome, inverse probability weighting, and doubly robust, which combines the regression adjustment or regression outcomes and inverse probability weighting. Right, so the example for doubly robust estimator, which comes directly from the paper itself, and this paper is shared with you on the shared folder. I will open it once we finish with this part. And you can see here that the derivation of this part is very similar to what we had, except for now we have several more terms. And so this you will undoubtedly see as the inverse probability weighting term that we have considered before, right? So this is our equivalent, let's put it this way, of yi bar, right? And then we have an adjustment term here, right? And obviously we take an average of that. So you see, there is nothing unfamiliar for you once you recall the estimation principles we considered in, again, in this part, estimation that I presented yesterday, right? And so that's the main important part. That was one of the aims. It's nearly impossible to give you all the methods that exist out there and all the extensions that are being developed in the differences in difference estimation. But once you understand principles for very simple traditional DAD approaches, the next ones that will come along, you will understand what they actually do and which methods they're built upon. Okay. Now, for example, this double robust estimator combines outcome regression, MD, and I will point to this in a Stata here, right? So this regression MD of X and inverse probability weighting, which I have just encircled here in red, right? And this double robust estimator is going to be consistent if either one outcome regression or inverse probability weighting is correctly specified. And inverse probability weighting is most probably correctly specified. So we're very happy to obtain the consistent estimate for double robust treatment estimator. Okay, what about aggregation? And I will pay quite a lot of attention to that. And you will see why it is important, because when we have multiple time periods and we have groups that were treated in different time periods because we have a staggered adoption, we really want to see in which year which effect actually took place and go from there. So the simple average here, given in formula 6.46, is the average over all possible groups that we have here. So groups in which the units were treated and in time periods that were treated, right? So what we will see here, this T is the calendar type, and I will pay attention to this when we consider Stata example here. Now, there is also a dynamic event study type aggregation. So that's the E here. And in Stata, you will see that's really easy to obtain it using a very simple command. And so this is a for particular event or the time of treatment. And then finally, we can aggregate the average treatment effects in groups, right? So we'll specify particular groups. We'll go from small g up to t, and we'll aggregate them in particular groups in which the observations were treated. Okay, so this is most important here. Now, I've noticed that some of you asked question yesterday about the R package. And obviously, R package is very attractive in a sense that it's a free software. So you can download the software for free, install it on multiple systems. And obviously, the DAD package is also a free one. So if you are to use both double robust and the Calvé and Santana type of estimator, you should be using the library DAD. And here is the simple sketch of the R code that you would use to provide estimation for treatment effects. And here you see it's GT, and top dynamic here refers to this type of aggregation. Okay, So this is a very simple example for our package. It handles pre-trend testing. Somebody asked yesterday about pre-trend testing. So that's what's implemented in this package. Covariates multiple regression types, right? So here estimation method is doubly robust, right? But you can use different types of estimation methods. So this is about R. Now, obviously, this training is dedicated to implementation in Stata. And so we are going to use the Stata package, which is called KNS. And KNS stands for this paper that I've cited here, Callaway and Pedro Santana in Journal of Econometrics 2021. I have put it on our shared folder so you can access it there. And so this is the command Callaway and Santana DID. And so this is the basic setup how you can have the dependent variable covariate. You have an I observation, time period, the group, or when it was the first treated, and then the method of estimation. So here, for example, that's a doubly robust estimator with inverse probability weighting that we have already seen this relatively complicated formula in equation 4.6.45, right? But obviously there is nothing you can't implement in the software. So that method estimates exactly the average treatment effect on the treated using this formula. Okay. So this is, and I'm going to look into different types of estimation for this command here. So obviously we have different options and estimators for this command, and we have different aggregation type, the calendar, the event, the group, the simple average, right? We'll consider all of them in our exercise next. Now, we have looked at two types of this estimators, and obviously the both drdid and csdid are powerful Stata commands for robust and flexible estimation using a modern difference and difference approaches. So they are your companion for estimating DIDs if you want to go beyond the two-period model, if you have multiple time periods, right? So it can handle the staggered treatment adoption. It can account for heterogeneous treatment effects and provide robust inference, right? So we have not talked about the statistical inference and standard error, but I have made you a small assumption, a small example of how you can do this in this estimation section. And I didn't want to overload you with theory, so you need to understand the principles. And if you're a applied user, you do not really need to understand all the mechanics, right? So you need to understand principles that I give you, but not all the mechanics, right? Okay, so what is the difference between these two commands, which are very useful? Well, first of all, the full name for double robust DID is double robust Zhao and Santana approach here. It's also published in Journal of Econometrics. So this is the two-period approach for two groups, right? Treated and control group. And you can apply it using the difference and difference framework with covariates, okay? Now, the key assumption for this command is the parallel trends and covariate balancing, meaning that you don't have covariates which have completely different distributional properties. And you may also think about this as an overlap assumption. Okay. Now, when you consider the Callaway and Santana estimator here, so this is the full name, it is a multi-period. So this is if you have more than two time periods, and it can handle the staggered treatment. right? So if everything happens in a single time period and the effects are homogeneous, we can recall, let me just go back to the two-way treatment effect, right? And we could say, so if treatment is homogeneous and you have only two time periods, you can by all means two-way fixed effects, and probably even if you don't have two time periods, we have seen it in our Granger type regressions, you can still use the fixed effects model. But if you have staggered treatment, yeah, it's not possible to use the two-way fixed effects. You need to make adjustments, right? And the assumption that this command does is the parallel trans by group and time, right? So this is for identification purposes. Okay, so this is what we've got for these two commands as the difference. Now, what they can and what they can't do. If you have a traditional or canonical 2x2 design, so you have two groups and two time periods, then obviously you need to use double robust DID approach, and that's the workhorse for you. And obviously it can handle different types of estimation. Now, if you have multiple time periods, so let me erase this. If you have multiple time periods, then obviously your choice for estimation is CS-DID, right? It can handle multiple time periods. It can handle staggered adoption. You can have a robust estimator, and you can estimate event study and dynamic effects. Okay, so that's basically it for the theoretical part that I wanted to talk to you about. I will save this file, and as I mentioned before, I will make it available online. Now, to streamline further the where's my Zoom? It's not that. I didn't see my share now. Oh, so now I see them. Okay, so let me just very quickly look at the chat. We have the link, okay? And so now I also want to take a look at, and let me just share the whole screen because this is what I'm gonna do using the Stata software. So can you confirm you see my whole screen here? Right, so here is the Stata.
Yes, we can see it, Professor.
Okay, perfect. Yes, great. So let me just also drag my Chrome here. So what I wanted to show to you is that this is the folder that I've shared with you. It's called 2025 July ADBI DAD. And here you will see the slides, or you have downloaded the slides that I've shared with you. Now, you can also see the literature, and here you have two papers at least. I will probably put more if there is request for that. So this is this Callaway and Santana approach that I've shown to you. Now, in the folder data, you have two data sets that I'm going to consider right now. So I advise you to download these two data sets and come along, because the whole analysis will be conducted using this Stata do file. So you can also download this Stata do file here, which I'm going to use, right? So this is basically your folder with the shared material that you can download and use in your training, and you can refer to later when you want to perform your own analysis. Okay, so let me just clear the screen here, and I will open the do file. And so here we are going to consider several things in Stata. As you can see, I'm using the Stata version 18 I know that Stata 19 is out, but I still don't have access to this. But if you have Stata 18, you can see that it works absolutely fine. So you shouldn't have any problems with this. Okay, so let me know if you can get the data which I have shown you, and we can get started. So the first data set here, NSWPSID. So this is the National Support Network demonstration project, which was conducted in 1970. This is a data set which is very convenient to show various aspects of estimation for causal analysis. And I'll tell you why. So you can download this data set here also from this website here. It is also used in Cameron and Trivedi microeconometrics textbook. So this is the not a made up data set you can download from this source as well. But I have put it conveniently for you on our shared folder. Okay. Now, what you need to do next is you need to specify where your data files lie. And so you need to change the working directory. So what you can do is you can go to menu file here in Stata, and you can click on this change working directory. If you do not really know how the cd command works, you can use this change working directory and then point to the downloads folder or whichever folder you were using to get your data set and your do file. Okay, so that should work absolutely fine for you. Right, so this is how you would do that. So let me just, without further ado, by the way, can I ask you, I'm very long time user of Stata, so I'm using this classical theme, which is green on black. Can you see it all right, or you think that it would be better if I changed the theme for, for a light theme so that it's black on white or something like this? Can you see it all right?
I think it's okay, Professor. We can see clearly.
This is okay. You can see. Okay, good.
Yes.
So good to know. All right. So I've let a little bit of time to let you download this data set. So I'm gonna start with the presentation. So first of all, let me just load this data set here, and I will use this, copy this here, paste it in the command line. So this is the data set we are going to use, and in my experience, it is much better if all the variables are lowercase. Some people prefer different types of conventions. Usually what I do is I rename all the variables that are in my data set to lowercase, and you can do this by running this line in number 13. So if you copy it here and say rename, so you just rename this asterisk means all of them to a lowercase, right? And so the name of each of these variables that you're going to have will be lowercase. And that's a good convention because in Stata, the large or capital letter or lowercase letter matter, and you can have two variables which have different cases for the variables, but they would be called exactly the same. So it's a good convention here to just have the same lowercase for all variables, but it's up to you. So in here, I'm going to demonstrate this, but it's up to you. Right. So what this data set gives you is that the treatment indicator variable treat here is defined as treat equals 1, so that's an indicator or a dummy variable, if the training is received, so observation is in the treated sample. Okay, so this is completely in line with the convention we used during our introduction yesterday. And then treat equals 0 will be the value for this dummy variable if no treatment was received, right? So we have a very simple scenario here where we have a binary treatment. And now you can just type describe if you want to look at what variables do you have in your sample. And so this is my first advice to you as an empirical researcher, is to always get familiar with your data set, because you really need to know what it is that you're going to estimate and what kind of data you have at hand. And this is how you can do this. Now, the variable treat here is treated, and we're going to look at the statistics later. We just need to look which kind of data we have. And so variable age is the age in years. Educ is the number of years of education. So this is how educated the person is. Black is the dummy variable, meaning that the person is black and 0 otherwise. Hispanic is if person is of Hispanic origin or not. MA or R is if person is married. And these are our important variables. Now, RE is our real earnings, annual earnings in 1974. RE75 is real earnings in 1975, and RE78, that's real earnings in 1978. Okay. Now, we also have two variables for the status of being unemployed in 1974 and 1975. And we have the scored age, scored education. We have the no degree if years of education is larger than 12. And we have the interaction between real earnings. No, so there's not an interaction. So that's the scored real earnings in 74, 75, and interaction now between the unemployment and being black and unemployment and having Hispanic origin. Okay, so this is the set of variables that we have in our data set, and I went through them with a purpose in so detail so that we know which types of variables we have. You see, we have individuals in our data set, and we have all types of characteristics on these individuals, and we want to see what would be the reason for them to be treated or not. We're going to estimate the propensity score. So let me make here slightly bigger, like 3. So the second type of inspection of your data would be browsing your data, and it just put it on a different screen for me. Okay, so I always advise my participants to really open the data set if they have not done this already, and just browse through the data. The difference between browse and the edit, right? So if you put edit, so this is where you can change the values, right? And so here at the top left, you can see that this is data editor in the edit mode. So I do not advise you to use the edit mode unless you want to paste some variable. I always advise my students to really browse the data and just see what kind of variables are available in their data set. And so here again, the same data sets we have treated, and you see it's a lot of zeros here, right? And if you scroll down, you will see that some of them get values of 1. It means that these observations are treated here. Okay, we have age of an individual, we have education. So we have different ages from 31, we have 54. So we have differently aged population here. We have education here again, 8, 11. The status of being Black origin or Hispanic origin, married, or some are singles, right? And so this is the real earnings in 1974. So 36,246, for example, here. Then in 75, this person has earned half of that, right? 17,000 instead of 36. And then this person remains at 17,000 again. Now we have unemployment status here. 0 means not unemployed, right? And we have square terms, no degree, and then square terms, right? So what we see here is that each and every row represents data on a single individual, right? So it's a wide panel format, if you will, if you're familiar with this terminology. And we'll use this fact because for some estimation, you need the data to be in a long format. So we will need to reshape this data set, okay? And I'll come to that. But before, let me just look at the balance for our data set. And for this, we are going to use the command which is called table, right? So we are just going to copy this whole line here, paste into the command line table, right? And so here we are going to look at the mean values because this is what we asked it to do. So the statistic is the mean for the variables, and we have just enumerated all the variables that we have in our sample. And we just also calculated the number of observations in here, right? So we have the number of observations. So we'll start from here. We have 2,490 observations that were not treated, meaning they did not undergo any training. And we have 185 observations that went through some type of training. Okay, so you see that the sample is quite unbalanced in terms of observations, and that's a typical setup, right? Because we usually don't have half-half. We are not in randomized controlled trial. Okay, so what we want to do next is we want to look at the to look at the effect is to simply compute the change over time in the earnings for those receiving the treatment of training. Now, this is the mean difference between 78 and 75 for those who actually were treated. And so what we can do here is if I just drop here mean only so that we have an output. And if I look at the summarize here, so this is the real earnings in 1978 of those who were treated, right? So we have only 185 observations. And the mean value is 6,300, and well, actually it needs to be, yeah, so 6,349. And if I do the same in the previous time period, right, it was 1,532. Okay, so this, we are interested in means. Why? Because this is the definition for the expected value. Okay, but what we also want to do is we want to look at the difference between this mean and this mean, right? And so I have coded this with help of locals, where I'm having a local RE mean for treated, and then I'm just displaying the difference between them. So what you can do, you can select these lines from 31 36, and then just click here, tools, execute selection do, or you can use the shortcut Control D. Okay, so when you do that, you will see it will calculate you the difference, right? And we see that those who were in treated group, their average earnings has increased by 4,817. Okay, now we do not know whether this difference is statistically significant, and we are going to look at that later on. Before that, what we want to do is to get a little bit more into the data set. We want to look at the plot of the densities of these two densities of 185 observations. So in line 41 here, we again summarizing the real earnings in 1978 for the treated group, and we know the mean. So this is just to plot these means here, as you can see in X line in line 51 and 52, right? So we just need to have the vertical lines representing the mean values. And here we're just going to use the K density in lines 49 and 50 to plot the kernel estimated densities for earnings in 1978 and 75, right? Okay, so let me just select the lines from 41 to 55 and execute everything together. Why we are doing this is because the local exists only within one execution. Once you have executed it, it does not exist anymore, right? So we need to perform the execution, note the local, and use it within the same estimation. Okay, so I'm just gonna select the lines from 41 to 55, go to Tools, and execute it, okay? So this will calculate the means, and that will also display it again displayed on Ron screen. So this is going to be the plot of two densities for real earnings in 1978 and 1975 for the treated group only with means. And what we can see, the blue density and the blue vertical line representing the mean are much to the right, implying that those that were treated actually in 1978 have obtained a much larger real earnings on average. Okay, so this is what we can get from here. Okay, let me just if we want to look at the statistical difference between these averages, right? Because we have the observational data, we can calculate the variable which we will call difference for difference, right? You can call it whatever you choose to call it. And then we'll use the command mean, which is shown in line 62, to test the difference statistically, right? So I will just execute these commands in line 61 and 62. And you see, so this is the same difference we have reported before, right? 4817, right? But now we also have the standard error. Number of observations in 185. We know that this is our treated sample. And we see that 95 confidence interval does not cover 0. So it means that this difference is statistically significant. Okay, so we can make the first conclusion that there is a significant increase in the mean. Right, so the limitation of this approach, however, is that earnings in general may have increased over time, right? Even if person hasn't been treated. So what we see in this increase that probably there was a tendency for increase in real earnings over that time period, and we do not take that into account, okay? So what we need to do next is we need to consider what's called the treatment control comparison. So we want to compare the post-treatment earnings with that in the control group, okay? So first of all, let's look at difference in mean test command. So this is done using the t-test. And so here we can look at the earnings which happen after the intervention by the treatment status. And we're going to take unequal variances for the t-test. Okay, so let me execute this. So the difference here is 15,000. The standard error is 657, and we see that confidence interval does not cover unity. Okay, so what it means here is that those that were treated earned much less than those that were not treated. Okay, so there is a significant difference between those that were and were not treated. And so right now what we want to do is we want to apply the difference in difference style estimator, because we want exactly to account for possibilities that there was increase in real earnings for those that did not undergo any treatment. Okay, so we have here the familiar averaged increase in treatment. So this is what we have already seen here, 4817. All right. Okay, so that's the average earnings increase in the treatment group. And now note how the line 91 is different from line 84. So here we are using this negation sign, not equal treat. And if you're not familiar with how Stata works, if our treat variable is the categorical, right? So that would be the same. So here in line 84, you see what I've done. So you can either say if treat, right? Or you can use if treat is equal to 1. That's exactly the same. Stata is going to understand this in exactly the same way. Compare this. Treat and treat equals 1, right? So that's exactly it. Because Stata, when it realizes that variable treat is the indicator variable, and it can only take two values, either 0 or 1, then you do not necessarily need to say that treat is equal to 1, because if you say if treat, it is going to consider that if treat were true, right? Now, by the same token, here, for example, you could say summarize if exclamation mark treat, meaning not treated, right? And that's going to be exactly the same as if you were to say not equal 1, right? So there are different ways of doing this. Or you can also say if treat is equal to 0, right? So all these three options are going to give you exactly the same result. So you can either say not treat, so meaning not true, right? And you have this 2,490 observations. Then you can also indicate a specific value that you want to exclude, and you say not equal to 1, right? Or you want to indicate a specific value that you want to have in your sample, and that's equals 0, right? So that's a programming notation, so you always need to use two equal signs. So my apologies to those who already knew that, but I just wanted to make sure that everybody is on the same page, right? So I'm just going to use this not equal treat so that we have the same, right? Okay, so let's look at the average earnings in the control group here by how much that they grew. So I will select the lines from 91 to 96, and I'm going to press Control D to execute everything together. And we see here that the average earnings in the control group grew by 2,500. Okay, so if we combine this two, right? So let me just execute them all. So in the treatment group, the average earnings increased by 4,800, and the average earnings in the control group grew by 2,490. So our suspicion was correct. The earnings were increased in the control group as well, right? So they were growing overall in the whole economy. So obviously we don't really want to capture that. So let's have a look at the calculation of this means in four groups. So we have the summary of earnings in 1978 in the treatment group. We have earnings in the 75 in the treatment group. We have earnings in 78 in the control group, which is not treated. And we have earnings in year 75 in the control group or not treated. Okay. And then what we are going to do in this line 125 to 137, we will plot the densities of four variables. Well, actually of two, but we are going to use the treat and not treat condition here. And we will also plot here for vertical lines, the X lines, which represent the mean for respective densities. Okay, and we'll put the labels and the title here. So let me select, this is a very long code that you will need to select from line 106 here, right? By the way, you can also select from 105, it doesn't matter because this is not going to be executed, all the way to 137. So in order for this code to work, you will need to select all these lines because in line 107, you save the mean value as a local variable, so it needs to be selected here. In line 110, you have a local variable, which is the mean for the treated in 1975 and so forth. So you need to select all the lines from the line 105 to 137, and then press Control D, and that is going to give you four densities. So you have the blue solid line would be treated in 1978, the blue dashed line would be the density, and the vertical line would be the mean in 1975 and so forth. Well, obviously what we can see here is that these four groups that we have in our 2x2 scenario, we cannot really see what's going on here, right? What have increased by how much. So what we are going to do is we are going to restrict the display range here. And so what I'm going to do here is I'm just going to use the same code. So I will calculate the means and save them as locals. But here, what I'm going to do is I'm going to restrict the X axis up to 50,000, right? So previously what we see here, our X axis goes to 150,000, and I want to restrict it to only, where is it? To 50,000, right? So let me see if this gives us a better representation of this means. So for me to get this restricted range, I need to select lines, or you need to select lines from 140 all the way down to 173. Okay, so you need to select these lines here, and then you can press Control D, and that is going to give you the graph, which now runs only until 50,000 as we have controlled it. right? So yeah, and the title also reflects this because we have done that. Okay, so now we can see a little bit better here. So first of all, let's consider the treated group, and that's the change from the blue line, right? And so from the dashed mean, which is the vertical dashed line here, to the solid line, we see that this is the increase in the expected earnings for the treated group. So this increase is quite big. If you look at the same increase for the control group, and this is the difference between the dashed red line and solid line, red line, then you see that the difference between those is much smaller, right? So what we actually do in our difference in difference approach is we are comparing these two differences. You see, again, we're stumbling across the terminology difference in differences, right? So one difference is the distance between the blue vertical lines, and the second difference is the distance between the red lines, right? So this is what difference estimator actually is doing. It compares these two differences. Okay, and now because we have this 2x2 design and we have data set up by observation, we can generate variable which we can actually actually have it here up, right? Yeah, so we actually have it in line 61, so we're just basically repeating the same thing here in line, where is it? We're repeating this in line 177, but that's just, again, much better for our understanding. So this first difference here, difference in means for treated group, would be the difference between the two vertical blue lines here. And this difference, if not treated, and this local difference mean in the control group, that's going to be the difference between the two vertical red lines here. Okay? And finally, we want to look at the difference between these two means. And this is going to be our difference in difference estimator. See, I wanted to lead you to understand what this difference in difference estimator actually entails and what the next regression is going to estimate for us. But this is basically the whole sense of the difference in difference estimator. Okay? So hopefully that gives you a little bit more understanding of that. And now, because we have this 2x2 design, we can also plot means. So we can look at the difference. So this is basically this lines 190 are exactly the same as those lines. We just need to save the locals. And we want to look at the plot of two densities for the difference for treated and non-treated, right? The difference between which we are actually looking at. So if you select the lines from the line 190 to 203, we are going to get the plot which shows us the density of difference by the treatment status with means. Okay, so we could have restricted the sample again, but we see that this red vertical line represents the difference between our red vertical lines in previous graph, and the blue one represents the difference between the blue lines, right? So what strikes us here is that we have pretty much symmetric distribution of the differences, and we see that we have both negative and positive differences, right? And I want to draw your attention to one of our slides we used here, where we said, was it in the intuition? Right, let me just go back to our slides and right, so this slide here. And when we introduced what we said, the gain, and we said the main gain from treatment would be the difference between the treated and control state. And for a particular unit, that's going to be a gain from the treatment. And what we also said at the bottom of the slide is that the gain could be positive for some eyes, for some observations or unit, and could be negative for others, right? And what we want to make sure is that it is actually significant on average, okay? So this is, again, you should not be shocked by seeing this particular graph of densities and say, look, why do we have negative values here? Right, because some of them will be negatively affected and some of them are going to be positively affected, right? And that's what we see here. Okay, dokie. So now that we understand how the how it works, we actually need to perform the difference in difference regression analysis as you would do in your own research. And so to do that, we want to work with a different type of data. Well, first of all, we need to reshape our data set because right now, let's remind ourselves that this is how our data set looks like. We have observation 1 here, and we have a treatment status that is going to be treated eventually, right? We have age of this individual, their education, their status. So these are time invariant characteristic of an individual, right? And so these are time variant characteristics of an individual. These are time variant individuals characteristics, right? And age actually is going to be, variant because every 3 years an individual becomes 3 years older, right? So there is nothing to do about that. So this is how our data set looks like. What we need to get from this data set is the long format. So the data set you see right now is the so-called wide format, where for each individual you see multiple values in different years. Now we need to have a long format, and so in order to achieve that, we will use the command reshape. So first of all, we will generate a variable which we call ID, and this underscore n just gives an order number, right? So if you execute this command in line 209, and then you again browse the data set, so at the very end, what you will see is that it will just create an ID, right? And for us, it does not actually matter which order number a particular individual is, because it's fully anonymized data set, so we don't actually care. We just need to have some kind of an ID variable, okay? So we create it like this. And now what we are going to do is we are going to reshape the data set to be long. And here we specify what would be our variable here. And here the I variable would be ID, which we have just created. And the J variable is going to be year. So this is the one which will be taken from this variable RE, right? Remember what we have in our data set. We have RE74, we have IE75, we have RE78. So Stata will look at variables which start with the two letters RE, and then put the rest of the names of these variables into the variable year. Okay, so let us execute this command. So if I do this, the Stata will give me a summary of what it did. So in the wide format, we had 2,675 observations. In the long format, I now have 8,025 observations. So each and every observation has a triple in size, right? So obviously now number of variables has reduced because we don't have three RE variables, right? So we have only one RE variable, and we also have an additional variable which is called year now, okay? So it takes on three values, and this is our X, I, J variables. You see we had RE74, RE75, and RE78. And in the long format, they have the name RE real earnings. Okay, so let us take a look at the variable, at the our data set now, again, for better understanding. So we see that this is our ID number one, and now it has three observations. You see the treatment status has been just expanded. So if it was 0, it stays 0, right? Age was 40, it remains to be 40. Education 8 remains to be 8 for each and every of them. But when we look at the real earnings, so they will be time varying. Okay, so that's how our data set has been reshaped. Okay, now in this format, we know that we can now run our difference in difference regression. Well, first of all, we do not want the year 1974, so we'll just drop this because we are not interested in that. The year 75 is a pre-treatment period, and the year 78 is post-treatment. So we are just going to generate a variable which we will call dpost. So this is a dummy variable post. And so this dummy variable is going to be equal to 1 if year is 1978. Okay, so let us generate this variable here. And what I want to do is I want to look at the table tabulate of this dpost variable. Okay, so let us see what we have here is that half of observation, exactly half, were in the pre-treatment state, and half of observations are in post-treatment state, right? So, and this is exactly it, because this is the balanced panel data, and we observe these number of observations in 1975, and we observe exactly the same number of observations in 1978. So our dpost variable is split half-half. Okay, so we are going to use the variable which we will call dummy variable treat, and so we'll just clone the variable treat because we already have it. Okay, so let me tabulate variable d treat here. So what we observe, we still have this number of observations, in total 5,350, but now what we see that this treated is only about 7% in our sample, okay? So this is highly unbalanced. Okay, so remember how we can run the difference in difference regression? So that was our first take on calculating the difference in difference estimator here. And I'm just going to show to you very quickly unconfoundedness, propensity score, Kidaki. Okay, so this is our main slide here, and what we are actually doing here is we are estimating equation 4.30. So we want to include the variable which is called treated here as a dummy variable. We want to include the variable which is called post here. And so let me just erase to avoid all this clutter here. So this is our variable d-treated. This is our variable d-post. This is the interaction between them, right? So this is the regression that we actually want to run. And some of you asked yesterday that they saw an application in literature that used only the interaction between treated and post. And if somebody was doing this, then it would not identify the four groups that we have here uniquely, and you would not be able to come up with the difference in difference uniquely if you omit this treated variable and this post variable. So in difference in difference regression, you necessarily need to have the treated dummy variable, the post dummy variable, and the interaction between the two. Okay. And this is what we are going to do. We are going to use this double pound operator in Stata, and we are going to use the variable variance covariance estimator, which is clustered at the ID level. So let me just run this regression here. And so what do we see is that our difference in difference estimator is given by the coefficient at the interaction term. And so this is our interaction term between dpost and dtreat, right? And it's equal to 2326. Does it ring a bell with you? I think it does, right? Because this is the difference in difference estimators that we have obtained here, right? And you see that it is actually equal up to the decimal point 2326, and we have here 0.505, right? So this way of estimating the linear regression, we have a clustered standard errors, right? So we have robust standard errors here. And why did we want to run this regression is because we not only have the average treatment effect on the treated estimator, but we also have the standard error in here, right? And we have the statistical test in here. And so what we can see that it is statistically significant. Okay. So if we want to add, so here, this is a regression with no controls. If you want to add some controls here, I will define the global variable here, my controls, and I will add them, or I will upend my regression here and run these two lines, 224 and 226. And this coefficient at the interaction term is still statistically significant, and it shows that those people who participated in training, their real earnings have actually increased by 2,326. Okay, right. So what we can also do is we can achieve the same, not with the two-way fixed effect regression, but we can also achieve it using the internal command by Stata, xtdid regress. So for this, you can look at the help file for xtdid regress later on, but this is not the purpose of doing it here, right? So first of all, if we want to use the command which has the prefix xt, we need to declare the data set to be panel data, and we do this by using this xtset variable. So we say that our panel variable is ID, and our time variable is year here, and we have years 75 and 78, so delta is 1 unit. And the syntax, so first of all, we need to create this interaction term artificially, because XTDID regress is not going to do this for us. So we are going to have this variable generated here. And finally, the syntax for XTDID regress is, in first parenthesis, we're saying which variable we want to use to explain what would be our treatment and post variable, and that's our interaction term that we have just generated in line 232. What is our group and what is our time variable? And this is here. Okay, so if I run this regression now, okay, so it will tell me something about the treatment and time information, right? So there is a control, there is treatment, okay? And we have so many in control group, so many in treatment group. We have the minimum values for the time and maximum values for the time. And it will also give me some summary about what type of regression has been just run. And what this command is going to give us is only ATT. Well, Stata has a terminology, average treatment effect on treated, as ATET. And we see this is exactly the same coefficient we have just seen in our previous regression, the robust standard error, right? So the AT estimate adjusted for panel effects and time effects here, right? Because we have specified them. Okay. So this is another way of running this XTDID regression. However, I wanted to draw attention to a different issue here, and that's the overlap assumption, right? So let us use this data set again and look at the propensity score, which I suggested we can right, I suggested that we can estimate this yeah. So we will use logit to estimate the propensity score here. So we'll include levels, squares, and interactions. Yeah. So we'll use all information we have in here, and we want to see whether we have any values that are close to 1 or vice versa, they are close to 0. Okay. So let me just run a regression of our dummy variable treat on the age, education of individual, their earnings in the previous year, the age squared, education squared earnings, the unemployment status in the previous year, right? And if we run these two lines here, okay, so that's going to be a logit estimator, right? So it converged all right. So we have 2,672 observations. We have age, education, real earnings, and then we have all sorts of squared and interaction terms in here, right? So, well, first is that 10 failures and 0 successes were completely determined, meaning that the probability of observation to be in a control group has been completely determined for 10 observations. And that's really bad because those observations turn out not to have a chance of being treated. So this is already violating our overlap assumption. So let us use the predict command here to generate variable pH, and let's look at the summary of these two groups of the variable th. So I have a detailed summary because I have the detail here, and we see that for control group where treat is equal to 0, half of observation have very low probability. So we have almost 2,500 observations, and only starting from 99th percentile, there is a half-half probability, and that's quite a low probability for the control group. So we may be distorting our estimator a little bit, right? And we do not really want to do that because the overlap assumption is not going to work. At the same time, what we can see for the treated group, starting from the 50th percentile, the observations have a very large probability, and we have a lot of observations that have a probability very close to 1. So that would indicate that the treated group may be violating the overlap assumption. So let me just generate a variable which I'm going to call flag, and that's going to be the observations where the predicted probability is lower than 0.1, or, so this vertical line is O, larger than 0.9, right? And so what we are going to see here is that only 15% of observations are not in this danger area that I have designated. So what I want to do is I want to plot the variables without any restrictions. So this is all observations here. And this is already a graph that we have seen before in a lecture, where the mean value for the propensity to be treated for the control group is very, very low, right? So you see the probability of being treated is very, very low. And we cannot actually allow that because we are violating the overlap assumption. Okay. By the way, this is an uncommented line 272, which you can use to save the graph. Okay. Okay. So let's exclude the flagged data. And so here I'm going to use the condition not flag, and we already are familiar with this syntax, right? We're just going to use the sample which is not equal for this variable. And so if we run these lines from 276 to 289, we are going to obtain a graph, which again we have seen in our lecture, and that's a density of predicted probability by treatment status. And here we see that we restrict it to be from 0.1, which is this left bound here, to 0.9, which is the right bound here. And so these are these 15% of observations that we have in our sample, which will not violate the overlap assumption. Now, what I've said during the lecture is that, look, this can, so let me just look at the marker. So this can lead to losing data on both control and treated observations, but we actually must do this because we do not want to have a situation where overlap assumption here is violated, right? So basically what happens is that in your empirical work, you necessarily need to do this exercise in order to see which observations can potentially violate the overlap assumption, which is essential for identification of average treatment effect. Okay, so you cannot just go around this and say, oh, well, I keep my fingers crossed and hope for the best. So once we do this, we again reshape the data set. And so we have here the same regression here. How many observations we have? We include all the observations that we had before. And now what we are going to add on top of this is our doubly robust estimator. And so we are going to use this command, the drdad, which I have advertised during the exercise. And the syntax requires that we include the I variable here, which is our ID, so that command understands that we have the panel data. We need to specify what is the time variable and what would be the treatment variable, and that's our dtreat. And finally, we are specifying which type of estimator we want to use, and we are going to use the inverse probability weighting. Okay, so let me just execute this command, right? So it will give you a summary what type of estimator that is. So there's double robust difference in difference. The outcome model is going to be weighted mean, and the treatment model is going to take into account the inverse probability. Again, we have all those formulas in the slides if you wish to check them. And what you can observe here is that it estimates exactly the same, estimates exactly the same difference because this is a very simple setup here, and it is still statistically significant. Okay, and so this is the only thing you're interested in, right? Now, if we add controls, and remember that my controls are defined here to have a number of time invariant observations. So if I run this, I'm still getting the same difference estimator, right? And I have a bunch of control variables in my regression here. Now, if I'm going to use the DID estimator here, and I will apply the inverse probability with controls, okay? You see that my difference estimator changes quite a bit. That's because it uses the weighted mean instead of the simple mean and inverse probability for the treatment model. It is still statistically significant here, but the effect is a bit larger, okay? Now, what we mentioned before is that it is really useful to exclude this flagged data, which may violate the assumption of the overlap. So what I'm going to do now is I'm going to run exactly the same regression as before, but now I will exclude this flag data. So my line 325 is going to give me the much smaller number of observations here. This is 798 in comparison to 5,350 before. And now what we will see is that this is my treatment effect. You see, it is much smaller than before, right? It is still statistically significant. The Z value is quite big, right? But this is the correct way of performing this analysis because we know that in this estimator here, we do not violate the overlap assumption. As I have advertised, you can estimate different types of models with this DID command. So we can use, for example, this double robust estimator, right? So the outcome model is going to be least squares instead of weighted mean, and our treatment model is inverse probability, right? So we still see the treatment effect being statistically significant. We can also use a different type of estimator here, which is the regression adjustment. And we remember what regression adjustment is, right? So I just want to draw attention very quickly to, so this estimation type was inverse probability weighting. Before that, there was the regression adjustment here, right? So it's a two-step procedure. And this is the one that is being implemented in this DR DID regression. Okay, so you see, we don't have anything unfamiliar here, and then we have the combination of regression adjustment and inverse probability, right? And so we still have a statistically significant average treatment effect on the treated. Okay. Now, what this command also allows to do is it allows looking at all possible estimates here. So if you look at the line 332, and you specify not a specific type of estimator, but you will specify all, it will perform all 6 possible estimators it has. Here's the summary at the bottom of this table, and it will give you the average treatment effect on treated for different types of estimator. Okay, so we have a strictly balanced panel. If you don't have a balanced panel, or if you work with a repeated cross-section, I think that we had this question yesterday, then what you need to do is you need to omit this IVAR option here, right? So if you look at the line 332, we specify the individual variable, right? And that's ID. If you omit it, right, we can still use this command, okay? We are going to lose some efficiency, right? So here, the standard error is here, 11. Here it's slightly smaller. For others, it's bigger, right? Especially for IPW, the standard error is much larger. It's 1400, whereas here it was only 1000. So what we see here is that if we do not take into account the panel structure that's available in our data set, then we are losing some efficiency in estimation, right? So if you have a balanced panel, if you have a canonical 2x2 scenario, then it is much better to specify this ID variable. Okay. So, right, we have variables which are clustered at the ID level, right? So obviously you can do this. So here it will just tell that variables are clustered at the ID level, right? And so that's much better than when you don't do that, right? Okay, so I think that this is all I wanted to say about the difference in difference. And again, my apologies to those who were more familiar with the difference in difference approach, and I've gone in greater detail again to explain the intuition and give you overview of what we are actually doing, rather than just running through commands and say, oh, execute this and run that regression and look at this coefficient. What I wanted to make sure is that we have full understanding what difference in differences does and what it is that we are estimating. And I hope it becomes clear for you. And as you move along in your education of difference in difference approach, and you will stumble along different new approaches, you will understand what has actually been estimated in here, right? So that's basically the whole purpose of this training, is not just to feed you with numerous approaches, but give you an understanding of what you're going to do. Okay, now let me just in the remaining time go through the example where you can estimate the difference in difference regression using the multiple time periods. And for this, I'm going to use this county teen employment data set. So I will urge you to use this MP data set, which is available here in the folder. So let me again draw your attention to this. So when you go to the data folder here, there is the second data set, MP, right? So I urge you to use this data set right now. And so I will do some labeling here. So this is a data set containing the log of teen employment in 500 counties in the US from 2004 to 2007. So county is a smaller unit, administrative unit than the state. And so this is the subset of the data set that has actually been used in the paper that I also put into the literature folder. right? So you have additional descriptions in that. Now, in this data set, I am going to have the variable year, which is the year of observation. Then we have the county unique identifier, which is my ID variable. Then we have the log of thousands of population in this particular county. We have the log of teen employment in the county. And we have the first treat is the variable, the particular year. I'm going to show that in greater detail because we want to look at the setup. So this is the year that the state introduced or raised its minimum wage. So we want to see whether this raising the minimum wage has any effect on employment. You see that there is a lot of these DID studies that actually show that we're interested in the earnings, we're interested in seeing whether some programs which are exogenous have changed the outcome variable. Okay, and we are going to declare the data set to be the panel data. So our panel variable is going to be county, and the time variable is going to be the year. So let me just use this data set, and I'm going to execute these lines from 351 all the way to 363. Now let me see if it works. Yeah, it works. All right. So I have 2,500 observations in my data set. So this is a description of the data set. It cuts only to 50 characters here. And I don't have a lot of variables, right? So I have only 6 variables in here. Year, county, log of population, log of employment, the time of treatment, and whether this county been treated in that year or not. Okay. So as I promised to you, it's really useful to look at the data set before you do any analysis. So I'm just going to go and browse this data set for the variables. You see, it's a very simple one. It has 6 variables, so there is not much to look at. So we have a year variable, which is very clear. County identifier, it doesn't tell us anything, right? It's just an ID so that we can make sure this is a panel data. There's a log of population, log of employment, and the year in which this particular county has been treated. Okay, so let's take a county. So this is our county 8001. And what you see in here is that we have a data from 2003 up to 2007, and we see that this county has been treated, or the minimum wage has been raised only in the very last year. So it was first treated in year 2007, and that's the observation. So let's have a look at this county here. Which ends with 23. So again, the data are available from 2003, the first column, to 2007. And we see that the first treat, the pre-last column here, is equal to 2006, right? So this county has been treated, i.e., its minimum wage has been raised in year 2006, okay? And so you can see that, so this county, for example, which ends with 11 here, it has never been treated, right? So this is in the terminology of the lecture that we had, is our C. So it may be treated somewhere in the future, but it is not treated in our sample. So this gives you an idea about how the data set is organized and what it is actually that we would like to analyze here. So let us look at the table of the year here. So we have already seen that. It goes from 2003 to 2007. In each and every year, we have 500 observations, and in total we have 2,500 observations. Now let us look at the first treated tabulation here. And so here, let me just make it slightly bigger so that it's on a screen. So we see here that we have 1,545 observations that were never treated. Okay? We have, and because each and every county is observed 5 times, so we can actually look at the display of 1545 divided by 5. So 309 counties here were never treated. Okay, in 2004 we have 100 divided by 5, 20 counties that were treated. 2006 we have 200 divided by 5, 40 counties that were treated, and 2007 we have the rest that were treated. You see that none of the county were treated in year 2005. Okay, so that's also quite important, because when we do the aggregation we need to understand what we actually did, right? So when we use the command xtdescribe, so we see that it's a balanced panel, right? So the pattern for all of them is 1 1 1 1 1. So each and every observation, so we have 500 observation, and all of them are observed in each of the years. Okay, so it's also very useful to look at how the variable is distributed. So this is log of employment here. And we see that this is pretty, symmetrically distributed. So this is how the variable should look like if it's all right. And so this is the population variable. It's also quite symmetrically distributed, so we don't have huge outliers. So we are fine with this. Okay. Now, in order to look at what can be done using this CS DID variable, it's very useful for you to look at the help variable. Okay, so it's again popped on a different screen for me. So let me just increase the font here so that we can all see, for example, 14, right? So the syntax for this command is as follows. We have a dependent variable, then we have a set of independent variables. We have a condition for subsampling. We have the ID variable. We have the time variable. We have the group variable, because remember, this is a group and time estimator, right? Let's remind ourselves what we are dealing with here. Right? So remember that the estimator that Callaway and Santana use is a group and time average treatment effect, right? So we have a group G and a time period T. So we need to specify this G variable, and G variable actually means the group or when it was treated for the first time. Okay. And then we have different options here, and most important of them will be the type of estimator that we are going to use, you see? And so even though that this is the Callaway and Santana estimator, it uses the ideas for double robust IMP estimator for inverse probability of tilting and weighted least squares. It can have the double robust inverse probability weighting, which we have already seen in the did command. Okay, and we have all other estimators that we can think of here, and you can try all of them when you experiment with this variable if you use it in your own research. Okay, so let me do this one estimator. I'm not going to concentrate, I'm going to concentrate on this rather than having the whole plethora of estimators that are available here. Now, given the syntax of the estimator, this is how we specify it. In the line 381, first we give the name of the command, then we have our dependent variable, and our interest lies in seeing whether the employment has been affected by the treatment. So our dependent variable is going to be the log of employment, of teen employment. Our covariate, our x, is going to be the population. So we just need to avoid any scale effects. So we're just going to account for the size of the county. Our ID variable is going to be the county ID. The time is going to be year. And our gvar, or the group variable, would be the variable when this county has been treated, or when the minimum wage has been raised in this county, right? And as for the method, I'm just going to use the IPW. And so this is the default estimation method. So I'm just going to specify it. Okay. So when I run this, what I'm going to get is pretty quick, right? So it's really quick. So it is going to tell me how many observations I have. And we are going to have a bunch of coefficients here. And if anything, these are all particular ATTs for different groups and different calendar years, right? So this table is actually quite informative, but it's not that we can, gain a lot from here. So this is the coefficients and standard errors, which later on, yeah, so let me just go again and show you what we have just estimated. So what we have estimated in here is what is given in this equation 6.45. So this is our double robust and IPV estimator here, right? So these are these ATTs that we have estimated, all right? And they were estimated quite quickly, as you have seen. But now we are actually interested in aggregation, right? So we have several types of aggregation here, the simple, the calendar, and the group. And again, I want to draw our attention to what we have here. We have a simple, calendar, and the group, right? So let's get down to that. So we have this, oh, before we do the aggregation, somebody asked yesterday, how can we test for parallel trend assumption, right? And this is easily done using this estat pre-trend. So if you execute this command here, right? So the null hypothesis here is that all pre-trend treatment are equal to 0. And because p-value is much larger than 10% or 0.10, we fail to reject this hypothesis. So we are good with our pretend assumption. Okay, so that's how easy you can do this using the testing procedure. Okay, let's look at the average, and the simple aggregation here for our whole sample would be this. And remember, this is the overall average treatment effect, right? It's not accounting for groups or times. And what we observe here is that average treatment effect is negative, meaning that introduction of minimum wage in states has led to lower employment among teens. Okay? So that's already quite significant. Minimum wage has led to lower employment. Now, if you want to aggregate this by calendar, by year, so we remember that we have several years in our observations. And so, for example, on average, it's statistically significant, right? For year 2004, it's not statistically significant. It is significant for 2005, 6, and 7. Okay, so that's already quite important for us to see that over time, the effect kicks in. In 2004, it's not there. Why? Because if you look at the data that we have, 2004 is actually the very first year, so probably we don't have enough observations to estimate that effect. Now, if you want to look at the event study dynamic effect that we have in our formula here, so we can look at pre-treatments, okay? So this is before treatment started, and you look at the p-values, and all of them are quite big, indicating that there is no anticipatory effect as you would have considered, right? And this is also encapsulated here is pre-treatment average, and you see the p-value is close to 1, implying that there is no anticipatory effect altogether, right? So somebody asked yesterday, how can we do this? And you can look at this coefficient here, average, the aggregation, and you can see that there is no anticipatory effect. If you look at the post average, yeah, it is statistically significant, right? So there is a significant decrease in log employment, but there is no anticipatory effect, okay? Right. Okay. So what we can do with this command here is we can also add some aggregation by using this AGG command, and we can use the while bootstrap to obtain robust standard errors here. For bootstrapping, you would usually use some seed, right? And so when we save this result in a file REF, we can then use it and look at what we have just obtained. Why we're using this is because you will see later we want to have some graphical representation. Okay, so what this file gives you, it gives you the effect for particular county. You see, now we don't have a panel data, we have a collapsed data. For each and every county, we have the observation, we have the effects, and we also have weights, which are later used in aggregation. Okay, so if you're interested in that, obviously these are the weights that are used later on, and obviously they are all non-zero when treatment has happened. Okay, they're zero when they were not treated. So what we can do now is we can look again at all these aggregations here, and we are going to get the same outputs as we got before, right? By time here, right? So not statistically significant, not no, now they actually all statistically significant for the calendar, right? So even in 2000 and no, t equals 0.66 is not statistically significant, and the confidence interval here includes 0, so it's not statistically significant, right? And then we have different groups here. Groups meaning the year in which they were actually treated. Okay, so I think that this is really important to understand that it's really important to understand that we want to look at this treatment effects by different groups as well. Now, if you want to look at the graphs, and that's a really important way of summarizing results, we can use the command which is called CSDID or plot. So let's run this. And oh, whoa. So just hang on. Why do we have all this? I only wanted this graph. Yes. So there are periods to treatment, and what we observe here is that 0 means that this is when treatment actually occurred. And this is actually what would need to be done in order to understand what it is actually that we want to estimate, right? So 2 years before, or even 3 years before treatment, we see that statistical significance is not there. And then 1 year after treatment, 2 years after treatment, and 3 years after treatment, the average treatment effect is statistically significant, and it's negative, meaning that employment has decreased. If you want to do this by group, and group means the year in which the minimum wage has been introduced, then we can look at this graph here, and we are putting them all on the single graph. Why? Because we want to see that, so this group 2004, obviously we don't have data before because our data starts only in year 2003. And so what we see here is that those who were treated in year 2004, the statistical significance of effect starts from the very beginning, right? In the first year, in the second year, and the third year. Now, you notice here that we don't have a group 2005, right? Because remember, we don't have anyone who were treated in year 2001, right? And finally, year 2007 here is a group which doesn't have any data post-treatment. So you see there is only one bar here in year 0, but nothing to the right from this, right? So all the treatment that we conclude here, couple of years after the treatment, actually is based on group of treated counties in year 2004. Okay. So finally, what we want to do is we want to look at the group by cohort, right? And so that's exactly what I said before. If you look at the average for those who were treated in the year 2004, we see that we observed the largest negative effect on employment. And this is mainly because we have much more data on those observations than we have on other observations. Okay. If you look at the year, right? So this is exactly the same situation here. After 2004, there is a strong and negative significant effect on log of employment. Okay. So let me just now turn on my camera because I'll probably take some questions from you. So I hope that, again, let me come back to the very beginning of my lecture slides, and come back to what was the aim and learning outcomes of this session. Is that I wanted to give you a lot of intuition about what differences approach is about, how you can get the treatment effect estimators, what are the modern approaches to different types of estimation, and how you can use Stata in your own approach, in your own empirical application of your approaches, right? So I hope you found this training useful for your own research, and I hope that I gave you ideas and foundations to further consider this application in your empirical research.
On behalf of ADBI, I thank Dr. Oleg for accepting our invitation and joining us to deliver the sessions on and providing the extensive training on this specific topic of difference in difference approach to the participants. And I'm very sure and hopeful that the participants have enjoyed, and they may have all got the deeper understanding of the topic with the practical knowledge of applying the DID approach in their research, and we look forward to the way that how you will be going to make effective use of this method in your research, and on maybe your ongoing work or the future works. So with this, before I close, so I would also like to acknowledge and thank the ADBI team for their support in successfully organizing the workshop for the last 2 days.